Hi guys, today we're going to finish up the chapter 14.2 notes, starting off with the 3 techniques used to measure reaction rate. Found on page 628, we have polarimetry, which is the reflection of light, which would be different for the reactants and the products, and so we can tell what sample is in there based on the polarity. The most common one, the second one, is spectroscopy, which has to do also with light. It is how light passes through a sample. We'll talk a bit more about that in a second. And then the last one is pressure measurement. So this would be if you are studying a gas reaction, and there are different moles of gas on the reactant versus the product side. For example, if you had this reaction up here, and if these were all gases, you would start out with 3 moles of gas and you'd end with 1, the pressure would go down. So we could tell by a decrease in pressure how much product is being formed. Spectroscopy is the most common one, and that is where we take a bunch of samples of the reaction at various times. So let's say this is T1, T2, and T3. We shine light through the sample and we detect how much light is able to pass through, which is called the transmittance, or sometimes we can measure how much light is absorbed by the sample, which is called absorbance. But we do that for all 3, and we could see if the product is, let's say, purple, as one of our examples is going to be. So if the product is purple, the darker it is, the less light will pass through. So the absorbance might go from like 0.8 down to 0.6 and down to 0.4. So we can tell by this decrease in absorbance how much the concentration of the product that's in there. Okay. All right, and we will talk more about that later, so don't worry too much. Just know those are the 3 ways that we measure the reaction rate, and we will actually do some measuring down the road. Reaction mechanisms. The mechanism is the way in which something occurs. So reaction mechanism, it's the step-by-step series or sequence of reactions. There's a large blank there. By which the overall chemical change occurs. So down here you see step 1 and step 2. These different steps are the mechanism of the net reaction. We'll get to that in a second. Intermediates are species. Okay, they're not reactants or products, so they're just a species in the equation there, that appear in some steps, but not in the net equation. So what is this net equation? The net equation is the overall reaction. It does not include any intermediates. And it's only what's present at the beginning, the very beginning of step 1, and what's present at the very end of your reaction. So basically what we're going to see here is some things are going to cancel out, like a math problem. If you have it on the left and on the right, it cancels out if it's there, and then it's used up. For example, CO2 right here. See, in step 1, we make 1 mole of carbon dioxide. And then in step 2, we use that 1 mole of carbon dioxide to make these 2 products. So the carbon dioxide is made and then used. Therefore, it's an intermediate. So we are going to cancel that out. And I also see, this is a little confusing, but stick with me. We have a oxygen here and oxygen here. So O2, you use up 1 mole in the step 1 reaction, but then you produce a half a mole in step 2. So overall, the net is going to be that you need a half of a mole of O2 total, okay, because you use 1 and then you get back a half of a mole. So the net equation is when you add these up, basically, and cancel out. So this 1/2 that's made leaves us with 1/2 up there. So the net equation is, let's add these up. Everything on the left, that's going to be carbon plus 1/2 O2 forms CO. So carbon burning, this is combustion, incompletely produces carbon monoxide, and this is what happens in car engines, and that's why they're dangerous, or sometimes in stoves inside, if you have a wood-burning stove. So carbon plus oxygen can produce carbon monoxide as well as carbon dioxide. And the intermediate for this reaction was CO2. The one that was produced and then used up is CO2. Okay, for example 2, we are to look at the mechanism on page 562. That doesn't sound right. Okay, so that is the incorrect page, so we're going to ignore that one for now, and we're going to use example 3. In example 3, we have a 3-step mechanism, so this reaction occurs in 3 steps, and the net is going to be what's present in the beginning and at the end of the reaction without including any of the intermediates. So what are the intermediates? I see 5 carbon dioxide being produced and 5 carbon dioxides being used. I also see there's 5 oxygens used in step 1 and another 3 is used in step 2. So that's a total of 8 oxygens being used and 8 are produced at the end. So that's an intermediate. And last but not least, we formed 6 waters and used them up. So we formed them in step 2 and used them in step 3. And so our net equation is going to be what's left. And I have 5 carbons, solid, plus 6 hydrogen gas. Moles yields contain C5H12. Okay, so that is our net, and the intermediates are O2, CO2, and H2O. Okay, a homogeneous reaction is a reaction whose reactants and products exist in a single phase, meaning all gases, all liquids, all solids really isn't an option, but I guess it probably could happen. A single phase. Okay, and collision theory. This one's a review, hopefully. You remember this stuff. In order for a reaction to occur, the molecules must first collide. If there is no collision, there will be no reaction. Not only do they have to bump into each other, but they have to bump into each other in the correct orientation. We talked a little bit about this the other day. They have to be lined up properly, and molecules have to have sufficient energy in order to react. Okay, so we are going to draw molecules that do not meet these requirements. So these are not going to be effective collisions. They're not going to react. If you have no collision, let's say you have molecule A and molecule B, and this one goes here, and this one goes here. If they never bump into each other, then A cannot react with B. And actually, we have to add a little bit more to this. So in order for these to react, let's say A and B have to collide directly, and we have these other atoms here that we're not worried about, these dark ones. Okay, we don't worry about. So an improper orientation would be if I had B colliding, it has to collide with A to react. So let's say that it's actually lined up this way. And if these two collide, the B and the black atom will not react in this example, so they're just going to bounce off from each other, so there'll be no reaction here. So no reaction there, no reaction there. Insufficient energy means they are lined up properly. So I have A lined up with B. They are going to collide, but if they're moving really slowly and they don't have enough energy to overcome the repulsion between their electron clouds, then they will just bounce back off of each other. So they're just going to bounce back after that, and there will be no reaction. Okay. Okay, so a quick visual of this. We have a simulation that's going to show us how these guys are colliding. So I have some of my reactants going in. This is the reaction A plus BC yields A, B, and C. So you can see that A and B have to stick together for the reaction to occur. And we are going to need a lot more energy than this. So I put in A, and let's put in some of the other reactant. I don't know what the lag is from, but there we go. Okay, so if these collided, there should be no way they're actually going to react. And let's see. They haven't collided yet. Oh, those two collided. But we have no products. Over here you can see I have 6 of each thing, and no products have been formed. They're moving very slowly. This is the total average energy of the green line, so it's very low. They need to have enough energy, sufficient energy, to get over this hill that we will talk about in a second. And they don't have that energy, so let's heat them up. Let's make them move a lot faster. Raising that total average energy up by increasing the temperature there. And if it's above the activation energy, then when they collide, oh, there we go. Now we have some product. So not only do they have to collide, but they have to collide in the correct orientation, and they have to have sufficient energy. So you see some bumping into each other, but we are still not having any reactions because they haven't bumped into each other just right. And, oh, now we do. There's one of our products. There's the other product, and you can see the 2 little C atoms that have separated off. Okay, so that is a demonstration of the correct orientation, correct energy. Oh, and it just unreacted. See, it went away. Alrighty. So that simulation was showing us activation energy as well as our collision theory up here. So when you put hydrogen in a balloon and have it in air surrounded by oxygen, it doesn't immediately combust. The combustion only happens if you add any kind of tiny little spark to this. Once you have a tiny spark, that reaction gives off enough energy to cause a chain reaction and the whole thing explodes. But it's not going to spontaneously combust without that spark. So why is that? Why don't the little hydrogens and oxygens just come together and rearrange and make water? Water is much more stable. It's a lot lower energy. It's like rolling downhill. So why does it not do that spontaneously? If you guys saw in the last simulation, we had our reactants. So let me try to draw water here. This is going to be exothermic. So our reactants for that example are H2 and O2, and they are pretty high up on the energy scale. This is going to be the progress or the course of the reaction, just meaning on the left we have the beginning of the reaction, and on the right we have the end of the reaction. And how it gets down here to H2O, it cannot just simply roll downhill. We have a little bump that those molecules need to get over in order to react. So picture, this is a metaphor or an analogy. This is not real life, but if this was going to get down here, we would have to first put in some energy to get it started, and then it would roll on its own down to the bottom of the hill here. Okay, so what is this little bump, this little bit that we need to add to get the reaction started is the energy that's needed to overcome electron repulsion. So remember that a reaction is just a rearrangement of the little atoms. So I have my H2 and my O2, and I want to rearrange them to form water. Okay, let's balance this out. We need, there we go. So I want these guys to rearrange and form my product. And in order to do that, we have to break the bond between the hydrogens. And also we have to get the electrons on the hydrogen to overlap with the electrons on the oxygen so that they share them over here. So that small amount of energy comparatively is called the activation energy. Okay, and I want you guys to remember that to break these bonds over here, we have to break apart the hydrogens and the oxygens. That is going to be an endothermic process of pulling them apart. When you form water, the bonds between the H and the O forming, that is an exothermic process. And because water is so very stable, it gives off a lot of energy when we form them. So we put a little bit of energy in to break these, and we get a lot of energy back out. And that's why overall that reaction is going to be, this one is exothermic. And the amount of energy that's given off is the difference between the start and the end. We call that delta E or delta H. That's the energy that will be given off. Okay, because we put in this little bit, but then it came back out. So let's say it went from, if we start at 0, and this goes up to 50, made up kilojoules here. If you put in 50, then you get 50 back. Okay, and the real change is from here down to here. All right, so you have to add a little energy to get the reaction started. This is activation energy. Okay, and then let's also do an endothermic example. So it's the exact opposite of what we had over here. Energy is increasing on the y-axis, and this is the progress of the reaction on the x-axis. So for endothermic, we're going to start at a lower energy and end at a higher energy. And we still have activation energy, so we're always going to have that little bump there. And this time to change delta E, it's going uphill. So you're going to have to put in whatever this value is from here to here. You put in that much energy to force the reaction to occur. Right? The activated complex is this strange, high energy, unstable, transitional structure that results from an effective collision. So the two molecules have collided in the correct orientation with the correct amount of energy, and the old bonds are breaking at the same time. Oops. I'm just going to put old bonds are breaking. Got ahead of myself. And new bonds are forming. So we have this weird in-between species where if I have my other simulation example where we had these two guys bumping into each other, and let's say this one left, as they bump into each other, and we're forming a new bond here, this bond is also breaking. So this weird thing where they're all stuck together and things are high energy and it's about to kind of fall apart and this one's going to come shooting off the side, this would be my activated complex. It's a complex. There's multiple things together here. And it's activated, it's ready to react. Another thing that could happen if it was right at the top of this hill, for example, this is my activated complex. It's the highest energy point. And at this point, it has enough energy. It can react, but it can also go back the opposite way and unreact. So the activated complex is the highest energy point, and actually we show it with an asterisk. So let me erase this guy. And the asterisk is the activated complex. The highest energy point of the reaction, where it's this weird transitional thing. We have bonds breaking and bonds forming at the same time, and it's very unstable. Right, that is it. And we will pick up here on Monday, and I hope you guys have a great weekend. See ya.